All right. So last week we kind of finished up confidence intervals and started kind of introducing the idea of hypothesis testing on Friday. That homework for Excel we just do at the end of the day today. So all of that is confidence intervals. Honestly, the main part of what you're doing in Excel there, what you're really exploiting in Excel is using that norm.s and t.i&b function. Other than that, we're really kind of using it to be our calculator for building that lower and upper bound for different confidence intervals. If you're having any kind of last minute questions on that, I'll be in my office today from 2:30 to 3:30, or you can send me an email. If it helps, you can even send me an email of what you have. If you have a question, I can take a look at it and then kind of get you a response back. I teach quite a bit on Mondays and Wednesdays, so if I don't get you a response right away, that's the reason. But other than that, we'll kind of pick up on where we left off on hypothesis testing. Are there any questions kind of for me before we get started? One thing I want to mention before I forget, tomorrow I will carve out some time where I'll go through one of the practice exams and basically kind of record myself working through the entire practice exam. So it'll like not me, but like my hand working through like on paper. So you won't just have the answers and even how they're worked out there, but you will have me working through every single one of them. Next Monday, we'll probably do some review and I'll probably go through the other practice exam in class. So we kind of have that one from in class, but the other one I'll get a video up there recording of me working through it as well. So, where did I put that? Okay. Why am I not? Oh, here it is. So I left off, and I don't even know if I used the term p-value, but we're thinking about this idea that if we had some assumed true value for a certain statistic, we could figure out how likely or unlikely it was we saw the sample value we did, or the sample mean we did, if what we assumed to be true was in fact true. So I think what I showed you was something like this. I think we had that example where the assumed true mean was 7%, or that the ABV, right, we want to test whether or not it was less than 7%. So we assumed, right, we wanted to test for whether or not it was less than 7. So we assumed the opposite was true. And we saw a sample mean of 4.5, right? So the probability that we saw the sample mean we did, if our assumption was true, right, that's going to be called the p-value. And we could find that because we know the sample mean should be normally distributed, as long as we get that sample size over 30, around whatever the true mean was. Well, we don't have the true mean, but we have an assumed true value for that. So we could turn this into a z-value. What we'll end up calling that is the z statistic. Once we have that value, we can look it up in the table and find the probability of seeing that or anything to the left, right? Well, the probability of seeing the test statistic that we did, or anything that's even further from that assumed true mean, that's going to be, well, that's going to represent our p-value. So this p-value is the probability we saw the sample mean that we did if what we assumed to be true was in fact true. Well, if this starts to get, the z-value starts to get large, or we start to get a high number of standard deviations away from that assumed true value, it's probably the case that what we assume to be true isn't in fact true, and that the true population mean, right, is probably something a little bit closer to whatever that sample mean that we saw was. So if this probability starts to fall below a threshold we set, then we would be okay rejecting, right? If the probability that I saw 4.5, if in fact the true mean was 7, that probability gets to be like 0.003. Well, that seems so unlikely, right? The probability of seeing that sample mean is so unlikely that this probably isn't the true value. We assume to be true is wrong. But how low is too low, right? Well, we're going to end up seeing the end of the class today, is that we're going to set this threshold that we'll call alpha. And we'll say, you know, if the probability of seeing the sample mean that we saw falls below 5% or falls below 1%, then we're okay rejecting. And it could be the case that what we assume to be true is in fact true and we're wrong, right? We shouldn't have rejected it. But that's okay because the probability is so low that we're okay making errors 1% of the time or 5% of the time, or whatever that threshold is we set. So this idea of finding that p-value, right, or the probability we saw, the sample mean we did, or anything further from that assumed true value, is going to look a little bit different for those three types of tests we talked about. So we talked about a left-tailed, a right-tailed, or a two-tailed test, or greater than, less than, not equal to test. So for the left-tailed test, that's the one that we kind of ended on. It's kind of easy because whatever z value or z statistic we find, we're just looking for the area to the left. Right? For a right-tailed test, whatever z statistic we find, well, we can look that up in the table, but the table gives us the area to the left. We're thinking, what's the probability I saw something this far above the assumed true mean or even further? So once we find that down in the table, we'd have to subtract it from 1. And kind of the trickier one is when we have a two-tailed test. Excuse me, I think we'll work through an example like this one today. If we had a two-tailed test, let's say instead, I just assume that that true mean is equal to 7. Well, then evidence on either side would go against the mean, right? If I saw 4.5, that goes against my assumed true null or assumed true value in the null. If I see 8.5, that goes against that assumed true value. So with a two-tailed test, it would have been equally as likely for me to see something just as far away from that assumed true mean on the other side of the distribution, and that would have went against the null as well. For those one-tailed tests, right, we saw something on the other side of the distribution that actually supported the null. Okay? So with a two-tailed test, it would have been equally as likely for me to see something this far away from my assumed true value on the other side, and that would have went against the null as well. So whatever area I find in my tail, using that test statistic, I have another area on the other side, so I have to take that area and multiply it by 2. Because that could have equally as been, it would have been equally as likely from one sample for me to see something on the other side. But I only have one sample, right? So I don't see the others. I only see evidence on one side because I only took one sample. But I know that it was equally as likely for me to see something that went against the null on the other side for a two-tailed test. So this is kind of the visual of, right, our left-tailed test, this green area representing our p-value, right-tailed test, here's our p-value, two-tailed test, we have two tails. So in practice, we can find one of them, because in practice, we only see one sample mean. So I can find that area to the left of it. For a two-tailed test, I have to remember, I've got another side as well, so I have to multiply that area by 2. And then ultimately, once I find my p-value, no matter what test I'm doing, all I do is compare it to this alpha value that I'm setting. This is the idea that I'm going to set this at the probability of seeing something for the sample mean that I did or anything more extreme. If that falls below a threshold that I set, then I'm okay rejecting the null. And typically this alpha value will be kind of like what we're doing with confidence intervals. It's going to correspond to the 90, 95, 99% levels. So our alpha kind of thresholds will be 0.1, 0.05, and 0.01. Same kind of thing we're doing with confidence intervals, right? Using those same 3 kind of benchmark thresholds. So I've got it written out a little bit more mathematically here, right? Kind of with greater than or less than signs, because it gets a little bit tricky when we're thinking about it mathematically, because for a left-tailed test, I need to kind of look for the area to the left of my test statistic. For a right-tailed test, I'm looking for the area to the right or greater than my test statistic. And for a two-tailed test, well, there I would just take the absolute value, because I just want to look in the kind of wherever is more extreme than my test statistic, or what's ever greater in absolute value. So the math looks a little bit trickier. I think kind of remembering that I'm just looking for the area in the left tail for a left-tailed test, or the area to the left of my test statistic, or this z statistic, this z value. Right-tailed test, I'm looking for the area in the right tail. Two-tailed test, I'm looking for whatever area is kind of more extreme or greater in absolute value than my test statistic, and then multiplying it by 2, right? And that's kind of, but it kind of depends, right? If I see value that's below my assumed true value, I have to look in the left tail for a two-tailed test. If I had seen something above that assumed true value, then I would have had to look to the area in that right tail, right? Or I always kind of say whatever is more extreme than my test statistic or larger in absolute value. So let's work through a couple. There we go. So I've got my steps, right? Oops, and then we'll kind of work through a couple of examples. So first thing I have to do is figure out what type of tailed test I have. How can I do that? Well, I have to look at my alternative hypothesis. So I need to figure out what my null and alternative are. That's the first step. Once I have that, I need to know, okay, what's this threshold of, so what probability am I okay with kind of rejecting the null? Then I compute that z statistic, that test statistic, or represents just kind of a z value, the number of standard deviations away I was from that assumed true mean. Then we'll compare that z statistic, not z statistic. We'll use that z statistic to find the p-value and then compare that p-value to alpha, right? If the p-value is less than alpha or less than that threshold I set, I'm okay rejecting the null. Okay? If it's not, then we say we failed to reject. We didn't find strong enough evidence to go against whatever I assumed that population mean was. So we left off with this example, and I might have even kind of worked through it. I can't remember. We'll work through it again and then kind of go to another problem. So we'll draw it over here. That was kind of general. We had this alternative hypothesis, which was one to test for whether or not that true mean was less than 7. So we stack the deck against ourselves, assume the opposite is true. Right? So the only evidence here that goes against the null is if we see something that's less than 7, right? Or on the left side of the distribution. We've got a less than sign in our alternative hypothesis. So this is a left-tailed test. So we use that assumed true mean of 7%. We see this sample mean of 4.5. We want to find the probability that we saw 4.5 or anything below that, if in fact what we assume to be true, the population mean of 7, is true. Right? If this is in fact true, what's the probability we saw the sample mean that we did, or anything even further than 7? Well, the next step, I guess, do I set an alpha here? Yeah, so I have an alpha of 0.05. So basically what I'm saying is, if the probability of seeing the sample mean that I did, or anything even further from that assumed true population mean of 7%, if that probability or that p-value falls below 5% or an alpha of 0.05, then I'm okay rejecting. So to figure out if that probability of seeing this or anything below it, or the area to the left, to figure out what that value actually is, we need to turn this into a z value, or what we call our z statistic. It's a test statistic coming from that standard normal distribution. Well, how can we do this? Basically, we use the exact same z formula that we did for sample means when we kind of knew the population mean. So to turn any sample mean value into a z value, we just took that sample mean, subtracted the true population mean, and divided by the standard deviation of that sample mean. Now, we knew the standard deviation of that sample mean was the square root of whatever the population variance was of the data we sampled from over our sample size. So the only thing that changes with hypothesis testing is we don't know that true population mean, but we have an assumed true value for it. So at this point, it's a matter of plugging our values. We know this sample mean is 4.5. We know the assumed true mean is 7. The thing I gave you here, that population variance, that would have to be given to you, right? And that's told you to be what, 1% here. And then we had a sample size of 36. Well, once I plug my values in, I've got everything I need to calculate what that z statistic is. So if I do that, I get negative 15. So this is a pretty extreme example, but I wanted to kind of show you like what a really extreme example would be. Any questions up to this point? So this is going to look very similar to what we were doing before. The only difference is we're using an assumed true value for that population. So we found sample evidence that's 15 standard deviations away from that assumed true value. I think maybe at this point we're starting to become comfortable working through some of these examples, knowing that to see something 15 standard deviations away from the mean is very unlikely. If I try to look this up in the table, what's going to be the problem? That z table only goes up to like -4, I think. And the area to the left of -4 is like 0.000. So this is even going to be even closer to 0, right? So I basically here have a p-value that's approximately 0. So if this p-value is approximately 0, the last step is, well, here I've got the critical value that we're going to talk about that maybe today, but definitely on Wednesday. So we can kind of don't read step 5 here. We'll kind of do that later today. What we're going to do then is compare that p-value to alpha. Our alpha was 0.05. Our p-value is pretty much 0. So our p-value is definitely less than alpha, and we're okay rejecting. Right? I mean, think about it this way. We assume that it was 7. The sample evidence we found was 15 standard deviations away from that. So if in fact what we assumed to be true was true, the likelihood of seeing the sample mean that we did was basically 0. Right? Well, if the probability of seeing the sample mean we did is basically 0, then it's probably what I assume to be true probably isn't true. Right? So I'm okay rejecting that null hypothesis. It's probably like more likely that the true mean is something much lower. So, I had some stupid mean to go along with the example. But the general idea is we're trying to determine whether or not the sample evidence we found varies enough from that assumed true value that we can reject it. Sometimes it won't. Like I imagine in this example, if I instead had found a sample mean of like 6.8 and then turned that into a z-value, well, that's not going to be very many standard deviations away from my assumed true value. And so it's probably going to have a test statistic that's low enough to where the p-value, right, is going to be pretty large. Well, the p-value is something like 0.4. That's not going to be less than my alpha of 0.05, and I would say I failed to reject. Because what I saw wasn't very inconsistent with what I assumed to be true. So let's work through one more example and we'll kind of turn it off. So let's say I've got a different example too. So, oh, this is, I think we did this one last class, at least just determining what the null alternative hypotheses are. So let's say that there's a sociologist and they want to test for whether or not the mean retirement age is different. I'm sure this is what, oh, nope, not different then. Greater than 67 here. I think I changed it a little bit. So we want to test for whether or not it's greater than 67. So whatever we're trying to find or whatever we're trying to test for, that's our alternative hypothesis. So that's kind of like the first thing you'll identify. So that alternative hypothesis is that mean retirement age greater than 67? So the next thing is we assume the opposite is true for the null, stack the deck against ourselves, and assume that that true mean is less than or equal to 67. Right? We said the null and the alternative hypothesis are like complements of each other. Okay? If I want to test to see whether or not the mean is greater than 67, the opposite of that is it's less than or equal to 67. So if, and this is where, I don't know if I kind of said this, so I'll use the other example to make this point first. And we'll think about this. If I can reject 7 as the true mean, I can reject any other value above that, right? Because if I saw sample evidence that was inconsistent enough to reject this as the true value, well then for any other value, like let's say I thought about the assumed true value of 8%. Well, then my sample mean should be normally distributed around that. And now the p-value is going to be something even smaller. So if I can reject that last value in my null hypothesis, I can reject every other value in that range as well. So we're always going to use whatever value we see in that null hypothesis. We're going to kind of test against that null No, for a right-tailed test, the lowest value in that range. For a left-tailed test, the highest value in that, or sorry. For a left-tailed test, the lowest value in the range. For a right-tailed test, the highest value. No, both of them would be lowest. Sorry. Yeah, lowest value in that range, okay, unless we had some negative values. So we'll use that assumed true mean of 67. If we can reject that with our sample evidence, we can reject every other value in that range as well. We saw a sample mean of what? 71. Okay. So what type of tailed test do we have here? We always look at the alternative hypothesis. We've got a greater than sign. So we say we have a greater than or a right-tailed test. Only evidence in the right tail would go against the null, right? If we see sample means above 67, that goes against the null. If we see anything in the left tail, like let's say I took my sample and I took a sample mean of 65. Well, that actually supports my null, so why would I reject it, right? We don't have to go through the steps in that, and that's easy. I know that I would fail to reject the null, right? So only evidence on the right side would go against the null when I have a right-tailed test. Okay? Any questions so far on here? Still just taking this in. So before I even do anything else, what I'm thinking about is my p-value will be the probability that I saw that sample mean of 71 or anything even further above that. Okay. So I want that area in the right tail. Okay. So right away, I mean, we're just thinking about normal distributions and some of the properties. What do I know my p-value has to be less than? So what would the area to the right of 67 be? That's the mean. Oh no. So if I have a normal distribution, and I'm looking at the mean, what areas to the left and right? 0.5, right? So I know that my p-value has to be something less than 0.5. If I'm looking at these right away, I can rule out p. So I know that my p-value is going to be less than 0.5. What's the actual value? I have to do a little bit more work. Right? And I have to convert that sample mean into a z-value, or what we call our z-statistic. It's kind of that. All that means we're, it's a z-value that we're using for this specific hypothesis test. Right? The statistic we're using for our test. And then once I have that z-value, I can find the area to the right. So from here, all I'm going to do is use that equation I had on the other side of the board to find my z-value. Now, I could do this in steps. So we look at that denominator down there. That just represents the standard deviation of my sample mean. So I could calculate that ahead of time if I really wanted to. So well, that would be the square root of my population variance, which is 81, over my sample size, what was that? 25. So what? This is the square root of, this would be what? 9 over 5. So we've got a standard deviation that's like a little bit less than 2. Right? 9/5 is a little bit less than 2. So if I'm just looking at this without doing the math first, if I'm 4 away and the standard deviation is just below 2, then my test statistic should be something right above 2, right? I'm a little bit more than 2 standard deviations away. If my standard deviation was exactly 2, this would translate to a z-value of 2. Right? I'm 4 away from the mean. Standard deviation is 2. I'd be 2 standard deviations above. But we're rounding a little bit egregiously here, so it's going to be something a little bit above 2. So from here, it's a matter of plugging in my value. So I've got 71 here was a sample mean value that I found. I'll subtract that assumed true mean. And then I'll divide by that standard deviation of my sample mean. So I calculated this ahead of time. And that sometimes makes it easier because I can just go ahead and plug in that 9/5. If I didn't calculate this ahead of time, it'd just be a matter of kind of plugging all my values in here in the denominator, right? Plugging in that square root of 81 over 25 in the denominator, doing it all at one time. So breaking it down into steps sometimes helps, makes it a little bit easier, but you don't have to do it. I did it in this example just to kind of show you that. So I plug this in my calculator. I forget exactly what this is. It's probably like 2.2, a little bit higher. 2.22. So I've got this z value 2.22. Yeah.
So I was wondering, what the first part was, I don't know if you mentioned it, but is there any way we could initially just cut out right away?
Yeah, so when we're looking at these, right? I said, what do we know this p-value has to be less than? We know the area to the right of that mean should be 0.5. So if we see something above that mean, the area to the right of that is going to have to be something less than 0.5. So if we look at these, we can rule out what? B right away. The other ones we can't really see.
Not even like not even point 0.122, would that be so small that you can't rule it out?
Well, let's think about it. We just saw sample evidence that's over 2 standard deviations away from what we assume to be true. We're probably not super comfortable or familiar yet, but if we're looking through these examples we worked through, seeing something 2 standard deviations above the mean is actually pretty far away, right? We said what? The probability something is more than 2 standard deviations away. I think the probability that we're within 2 standard deviations above or below is, what was that going to be? It's going to be like 0.9, no, close to 0.95, just under 0.95. And so the probability we see something further than 2 is like less than 0.05. So this is actually pretty unlikely we saw something this high. So the p-value, or that probability being 0.01, is actually pretty likely. In fact, I think if we work through this one, if I look up 2.22 in my standard normal district or standard normal table, so if I go here, I got to zoom in because no one can read that. So we go down here, 2.22. So that second decimal is that 0.02. So we're going to stay in this column. 2.22. The area to the left is 0.9868. Okay. So this is where, kind of thinking about this ahead of time, I just found the area to the left is 0.9868. If I was kind of working quickly, I might say, okay, I've got my answer. I found that probability. But if I had this drawn out, I would remember, well, I already said that it has to be less than 0.5. I'm looking for the area to the right. So once I look up that value of 2.22, the probability I saw something 2.22 standard deviations above that assumed true value, or something even further, would be 1 minus that 0.98. And then I think we actually get that 0.0132 if we subtract that from 1. So quite often, I mean, it's hard to say with just looking at the values, because really, once we convert these into z values, we don't just care if we're 5 away from the mean or 100 away from the mean. We care about how many standard deviations away we are. So once we look at that standard deviation, we can see, oh, okay, yeah, being 4 away from the mean is being about 2 standard deviations, and that's pretty far. Right? In fact, the probability that we are that far away is close to 1% here. Okay? So we have a relatively low p-value, which means that we can start to reject at most levels. Now, if I'm looking at this p-value, or the probability I saw, the sample evidence that I did, if what I assumed to be true was in fact true, that probability is really low, 0.0132. However, if I'm making my rejection decision, and I'll do this over here since I don't want to erase anything over there yet. You can start to think about what levels could I reject the null at in this example. Well, we only reject if the p-value is less than alpha. So this is kind of, if you want to write, right, this is the only time we reject. One nice thing on my confidence intervals, I have to build like all these different confidence levels. Once I get that p-value, I can start to compare to all of the levels of alpha, right? So once I have that p-value of 0.0132, would that be less than an alpha of 0.1? Yeah. So I can reject at what we call kind of the 10% significance level, which corresponds to like the 90% confidence level. So I can reject based off the sample evidence I found with 90% confidence. Is that p-value of 0.0132 less than an alpha of 0.05? Yeah. So I can reject with what we say 5% significance, or think about it as I can reject with 95% confidence. So those are kind of our first two benchmarks. Our last benchmark would be 0.01, or not less than 0.01, just barely above it, right? But it's not less than, right? We're close, but not quite. So we would say here we fail to reject with 1% significance, or we cannot reject with 99% confidence. Or I shouldn't say we cannot reject at the 99% confidence level. Questions on? So once we get that p-value, it's just a matter of comparing it to those different alphas and seeing what levels could I reject this null hypothesis, or this assumed true value for the mean at, and what level might I fail to reject that. Question? Just think about this somehow. We'll work through this one and I'll kind of go into something else. So I want to try to see if you guys can kind of work on this exactly where you're at. I understand it might be difficult, and I'll kind of help walk you through this a little bit. But I want you to kind of try to walk along. So we've got another example where I've got back to school spending amount. So some group said that the average back to school spending is $606.40. You're not sure, you don't really necessarily think that that seems right, or you're just curious, and you think that the true value differs from this amount. So if I think the true value differs from this amount, which one of the, I've got, take a sample and see 30 families, the sample mean is 622. So it varies a little bit from that stated amount, and I was given a population variance somehow. Wait a second, this isn't very realistic, but we'll kind of look at examples where what happens when we have a sample variance. So if I'm trying to test for whether or not it varies or it differs from that stated $606, what I'm thinking about there is I want to test to see, is that true mean something other than 606? So is it not equal to? So I assume the opposite is true, which is that it is equal to that $606. So we've got a two-tailed test here, right? If I see evidence on either side, that would go against my null hypothesis. My null hypothesis now is just that it's equal to a very specific amount. So you got a two-tailed test. I'm going to get this to switch for me. All right. What's the p-value of this test going to be? So this is the one that this is what I want you to work on. So we've got a two-tailed test. So I've got this sample mean of 622. I'm going to want to convert that, and I'll write the z-statistic equation here up on the board. We want to test or turn that 622 into a z-value. Look that value up in the table. Now for a two-tailed test, once I find my area in the tail, we said that it was just as likely that I saw sample evidence on either side that went against the null. So once I find that area in the tail, we said we had to do one more thing for a two-tailed test, which was multiply it by 2. So you'll turn that value of 622 into a z-score using this equation. Use that z-value, find the probability you saw that or anything more extreme, or that area in that upper right tail, and then kind of multiply by 2. So I'll let you guys work on this one for a little bit. And then we'll kind of come back together and talk about it. So talk to people around you, work with people around you. Maybe they understand something you don't. Give you a couple, 2-3 minutes to work on this. So remember, we're looking for that p-value. In the process of finding that p-value, you'll have to first find that test statistic or that z-statistic. Can I go to that 6-minute mark and we'll talk about this? All right. If you haven't gotten an answer, and take your best guess here. Is it showing up on the refaf okay? Okay, just making sure. All right, make sure you get your answer. I'm going to close it out here. Okay, so we have a two-tailed test. We already identified that. The value that we had in that null hypothesis that we were looking at was, is it equal to that $606.40? So if that value is in fact the true mean, our sample mean should be centered around that, normally distributed around. We saw what, a sample mean of 622.85. So before we even do anything we think about, we're looking for the probability we saw that or anything more extreme. But it would have been equally as likely for us to see sample evidence on the other side of the distribution that also went against the null. So this is going to be the one that once we find this area, we know it would have been equally as likely for us to see something over here on the other side of the distribution. So we'll have to multiply it by, it looks like alpha, multiply it by 2 in order to get, it's just like 0.24. Multiply this by 2 in order to get our final p-value. So to find that area in the right tail, we'll turn that value for our sample mean into a z-score or into a z-statistic, as we kind of reference these hypothesis testing z-values as. So at this point, all I'm doing is plugging everything in this equation, everything I need, right? I've got this sample mean of 622 something. I've got my assumed true mean of 606.40. I was told my population variance, I think I have my sample size is 30. So once I plug everything in here, it's a matter of being able to use my calculator. Now, one thing that can help is find what's in the denominator first, find that standard deviation of your sample mean. So you only have to plug one value in there. You don't have to worry about as many parentheses. So if I plug everything in here, I'm going to go out on the limb and guess I find about 1.83 to 1.84. No. What do I get? That's wrong. What do I get? 11. Oh, shouldn't be 11. 1.39. 1.38. That sounds about right. So I find that z-value of 1.38. I look that up in my standard normal table, right? 1.3, go over to the 8 column. So kind of walk through that real quick. Go up here. Maybe I can get everything. Oh, there we go. 1.3. Oh, 1.39. Okay. So 1.39, 0.9177. Okay. So when I look this up, this z statistic of 1.39, the table tells me the area to the left, right? Well, I wanted the area to the right, right? The problem is saying that sample mean or anything greater. So I have to subtract that from 1. That would give me the area in this right tail, right? So that's what, 0.0823. But that's not my final p-value because I had a two-tailed test. So I then need to multiply that by 2. Right? Once I multiply that 0.0823 by 2, I get that 0.16. So my final p-value there is 0.16, whatever, 46. Any questions over anything in that process? Any questions if something changed or why I did a certain thing? So that last step of multiplying by 2, that's only when we have a two-tailed test, because for the other test, well, if I'd seen sample evidence on the other side, that would actually support the null, right? Just that when we have a two-tailed test, evidence on either side kind of goes against that null hypothesis. So we know whatever sample evidence we saw, we only see one sample, we would have to kind of multiply the two, because it would have been equally as likely we saw something that went against the null on the other side of the distribution. So we worked through this one. We found that z statistic. We went and looked it up on that z table. Found the area to the left was 0.9177. We wanted the area more extreme than our test statistics, so the area to the right. So we had to subtract that from 1, and then it was a two-tailed test. So once we found the area in that one tail, we had to multiply by 2. Now, if I'm thinking about these answers, which one of these should I have been able to rule out right away? The p-value represents a probability, right? So A, we should have been able to rule out right away. Now, if I looked that value up, that z value in the table, and I found 0.91, said, okay, cool, it's a two-tailed test, I need to multiply it by 2. I would have got that 1.8 value. But that would remind me, oh yeah, I'm looking for a probability, it can't be over 1.8, so I must have messed up. Oh yeah, that's just the area to the left of that z value. I wanted the area to the right, so I have to then subtract it from 1 and then multiply by 2. All right. Any questions here before I? One more thing I kind of want to point out. I might introduce something real quick. On Wednesday. So I could use either of those p-values. We kind of already walked through this with the first one, and basically making my rejection decision at different levels of alpha. Well, we did that for the first example, but I can do it for the second one as well. The p-value as high as 0.16. Well, that would be less than alpha of 0.2. I use that just to show you that, yeah, I guess at the 20% significance level or at 80% confidence, I could reject the null in this second example. But if I wanted to make a rejection decision at my normal kind of alphas of 0.1, 0.05, and 0.01, and I found that p-value of 0.1646, well, that's not going to be less than any of my alpha values. So that would actually be an example where for my benchmark value alphas, right, or my 90, 95, 99% confidence levels, I actually failed to reject at all 3 of them, right? So because I'm not less than any of those, I failed to reject at all 3. This slide, I kind of changed that benchmark. Instead of 0.1, I used 0.2 up there just to show that if we go back far enough, we could reject at some level of confidence. And that's really the value of a p-value, right? Is that it's actually telling me that's the last level of confidence that you could reject it, right? Because as I'm working through this, right, okay, with a p-value of 0.16, I can reject it to 0.2, the alpha of 0.2, or 20% significance level, or 80% confidence. I can reject it at 0.18, 0.17, 0.165, right? I can reject at any level below my p-value, right? As soon as I start to think about levels though that go above that p-value, I can't reject at any of those. So it's almost like my cutoff rejection level, right? I can reject at any alpha level, right, below 0.1646 or my p-value. And I would fail to reject whenever alpha gets above that. So that's kind of what my p-value is telling me. It's almost like my threshold kind of level that I could reject at. Any questions on that? So I think we'll talk about type 1, type 2 errors next class. And then we'll go into how we do this hypothesis testing, but for proportions. Right? Now, I'll also introduce another approach to hypothesis testing, which is called the critical value approach. So hopefully we're kind of feeling a little more, we worked through some examples of the t-value approach today. I'll show you how we use the critical value approach, but also show you proportion examples at the same time on Wednesday. And then Friday, we'll look at, well, what happens when we only have the sample variance? And then that should be it going into that exam next Wednesday. So it should leave Monday open for us to kind of just do review. I'll film that additional video of me going through one of the practice exams. You'll have that as well. Other than that, no questions for me. I'll let you guys get out of here, and I will see you on Wednesday.